Okay, so this is geochemistry exam feedback for 2016. So if you did the geochemistry exam and you wanted to find out what we were looking for, then this is for you. And if you're doing the geochemistry exam in the future, then this might be a good idea for you to listen through this video and see if what you think an answer is what we're actually looking for. So hi, this is me. So this video is going to be just about my 3 questions, so 1, 3 and 5 of the 2016 exam. So these are those questions. So there's one question here about explaining why kinetic isotope fractionation happens. One question, which was this one here, which was basically asking you to design a sampling and measurement strategy to see how you could answer a geochemical problem, in this case lead in a school playground. And then the final question, class 5, was a little bit more structured, that kind of like walked you through a calculation and then asked you to say something about those results, basically. Okay, so before we move on, I just want to point out some of the really fundamental mistakes that quite a lot of people made. So some people did really well in the exam, which I was very pleased about. So if you did really well in the exam, well done, thank you. But quite a lot of people didn't do so well for some, I guess, tactical reasons. So one of the main reasons for not getting marks is you didn't answer the question. Okay, so you made up some other question which was about maybe some past year's exam or something that you had actually revised. That doesn't get any marks. Sorry about that, but you have to answer the specific question that we asked you to. And then the other part was basically quite a lot of the questions have explicitly parts A, B, C, but others are less explicit, but they are nonetheless still divided up into parts. So we'll go through and have a look at some examples of that. But it's really, you have to answer all of the parts of the question to get all of the marks. And then there's this last bit about critical analysis. So this is something that's kind of really key towards the honours level university. This is really saying, well, this is the answer, but there are these other things that you might want to say in terms of how valid that answer is, or any other caveats to that, assumptions that you've made to come up with that answer, and basically assessing the robustness or any positive alternatives are what we're really looking for as to show that you're a really good student, which I'm sure you are. Right, so going on now to the actual questions, kind of one by one. So the first one, using appropriate thermodynamic arguments and specific geochemical examples, explain why some chemical reactions have a kinetic isotope fractionation. Okay, so we're just going to split that up into these parts. Okay, so really this question has 3 parts of it that you have to answer. One is, why do chemical reactions have a kinetic isotope fractionation? So the key parts of this thing here, I'll just give myself a little pen. Okay, the key, I've disappeared here. So the key questions are why, and then it's, so why do those reactions? So you need to explain not just kind of that they happen, but explain some of the mechanism behind that. And then the other things are, you have to include thermodynamic arguments, and give specific geochemical examples. And I've just put the S here in. I'm going to get rid of this pointer because I can't see what's going with the pointer. Give me the pointer. Pointer options. Okay, so again, this is here examples. You have to have more than one example because examples is plural. Okay, so for the first kind of part, it might be an idea to explain broadly before you go on to the specifics of kinetic isotope fractionation, why there is isotope fractionation at all, and then go on to the specifics of kinetic isotope fractionation. So this is a little bit of a trap here in that some people just went off and explained in quite detail equilibrium isotope fractionation, which is not what the question is asking. So that didn't get many marks, but explaining why there's isotope fractionation and then the kinetic isotope part of that is what we're really looking for here. So if you go back to some of the lecture material, I mean, this is really, it comes down to bond strength. So these are some slides from some lectures. So the bond can be thought of as kind of a spring, and the frequency at which that bond vibrates is given by these equations down here, which have this term mu in, and mu is the reduced mass. So it's basically the vibrational frequency of the bond is dependent on the mass of the isotopes at the end of that bond. Okay, it's quite simplified in this case, very simple kind of bond that only vibrates in one direction, but nonetheless this kind of holds true for all bond vibrations. Okay, and that's important because this bond vibration actually determines the strength of the bond. So it determines the kind of the lowest possible energy state of that bond. Okay, through this kind of Planck's equation up here. So this effectively means that the heavier isotopes can end up further down into this potential well here. So they can get lower and lower down, and that means ultimately that bonds with heavy isotopes are stronger. Okay. Now this is where some people went off into a kind of an argument about equilibrium isotope fractionation, where the heavy isotopes go into the stronger bonds as well, but that's not really what this this question was really focused on. It was about the kinetic effects, and that the principal kinetic effect is that if you have different strength bonds caused by having different isotopes in your molecules, then that means that those different bonds will have different activation energies to break. Okay, which means that reactions involving those bonds will happen at different rates. So this is the Arrhenius equation. So the activation energy here, which is dependent on bond strength. Okay, so it means that the reaction rate will be slower if you have heavier isotopes, if you have a higher activation energy, and that's really key. So we go on to moving towards into some of the examples to help explain this a little bit better now. So this is an example of a reaction, and this is a really key point. This is a reaction that only goes one direction. Okay, so this is photosynthesis, so there's no back reaction to photosynthesis, and quite often this reaction doesn't go to completion, so we don't use all of the CO2 in the atmosphere to form all of the organic matter. Okay, so what happens here is we take these reactants, we form products, but because the reaction rate of this equation here, which is made up of all the light isotopes, is faster than the reaction rate of this guy, which is all of the heavier isotopes, this means that, well, first of all, if these reactions went to completion, if we ended up taking all of this, converting it into all of that, and all of that to all of this, the ratio of light oxygen to heavy oxygen in the reactants will be the same as the products if we've converted all of this stuff into this stuff. But if we don't complete the reaction, more of the light isotopes will be converted into products. So in this case, the lighter isotopes will be preferentially enriched if the reaction doesn't finish. So that's a really key point of this question. The reactions have to be one direction and they have to not go to completion. Okay. Quite a lot of you missed out on this little addition to explaining kinetic isotope fractionation. So some reactions, particularly reactions that happen in cells, okay, some of the chemicals or some of the reactants involved in those reactions have to diffuse through cell membranes across space in the cell to get from one part to the other, and that diffusion is dependent on the mass. Okay, just because of the the kinetic energy of, well, so any one temperature, the kinetic energy of all of the molecules or atoms or whatever is kind of involved in the reaction, they will all be approximately the same. So they'll be evenly distributed. But if the kinetic energy is the same, then the velocity of the lighter isotopes will be higher. Okay, so because the velocity of lighter isotopes is higher, that means that they'll be able to diffuse faster. Okay, so any chemical process that has diffusion as part of its kind of reaction pathways, the products will be enriched in the lighter isotope if they don't go to completion. Okay, so moving on to now some of the examples that you could have used, and I mean there's almost unlimited amount of examples that you could have used to explain this. So particularly good ones are those involved in kind of biological cycles, because these are quite often unidirectional reactions that don't go to completion. So we've got kind of carbon or any nutrient moving up a food web. Okay, will be preferentially enriched in the lighter isotopes as we move up the trophic levels. Another more specific example may be methanogenesis, which has multiple steps. Okay, I wouldn't expect you to know all of the detail of these kind of individual reactions. I mean, I don't know all the details of those reactions. I couldn't even hope to start to memorize all of these hideously complex molecules. But it has a number of steps, which means that it has a number of times that the lighter isotopes are enriched, which means that the product, which is methane, is very, very light compared to the reactant CO2. One example that was used quite a lot was the oxygen isotopes of rainfall, in that the lighter isotopes are preferentially evaporated, they move over land, and the heavy isotopes are preferentially condensed out, leaving the remaining clouds and rainfall at high latitudes really, really enriched in the lighter isotopes. Now this is a case where this is where you could have brought in a little bit of that critical analysis, in that those statements I made about these steps here are true, but there was a large component of the isotope fractionation between water and water vapor. That is an equilibrium isotope fractionation. Okay, some of it is kinetic, but there's a large amount which is equilibrium. So if you'd have mentioned that and explained that some is equilibrium, quite a lot is kinetic, why, what controls that, that would have been good. Okay, to have that little bit of, this is an example of kinetic isotope fraction, but there is also an equilibrium effect here as well. Okay, almost everybody missed out on that. Okay, so I'm going to skip over question 3 and move on to question 5 now. So question 3, very few people answered, and so more people presumably interested in question 5. I'll come on to 3 later. This is the question, so it's basically asking you to use this temperature equation for the difference between oxygen isotopes in water and in carbonate that precipitates out from it, okay, to do a number of things. So the first part is, what is the oxygen isotope composition of the water that the forams grew in? Okay, and we give you the equation, a whole bunch of information here. The next part is saying that there are some other samples that we found that have a different isotope ratio, what temperature of the water they grew at. So once again we have the paleotemperature equation, there's a bunch of information which you have to extract from your previous answer. And then the last part is where most of the marks were for this question, so comment on the assumptions that are made in this approach. Okay, so we'll just whiz through some of these. So first of all, what was the oxygen isotope composition of the water that these forams grew in? So what we're asking you for is to work out this value here. Okay, we give you 5 degrees C for this number here, we give you +2 for this value here, so all you have to do is rearrange this equation. Okay, that's very simple, that's why there aren't any marks for it. The answer was minus 0.1125. Now, many people got this, many people didn't get it because they made some simple maths errors rearranging this equation here. So I won't go into exactly how to rearrange it now, it should be fairly straightforward. But one of the things that fewer people did was that if you look at this answer that I've written down here, it's a little bit inappropriate. Okay, so I've quoted it here to 4 significant figures, but the information that I've been given is only to 2 significant figures. Okay, so I'm quoting an answer to a higher precision than I actually know. Okay, so in this case there are also some other constants in these equations which are given to higher degrees of precision, but doing questions like this you shouldn't use the constants in the equations to determine the precision of your answer, because every time you calculate a number with those same constants, doesn't matter what the precision of them is, if it is slightly wrong there'll be a systematic offset. but there won't be a systematic offset between values that you calculate using different input parameters rather than different constants. Okay, so in this case, look at the input parameters that we're given. The measurement has got a 2 significant figures precision, so we should really quote our answer to 2 significant figures. Okay, now moving on to the second part of the question, it's very similar. We have a last glacial sample now rather than a modern sample, and it's measured to have carbon isotope composition of plus 3.5. Okay, so now all we're asking you to do is calculate the temperature. Okay, and once again, super straightforward. You just plug your new value into this equation here. Okay, using the value of water that you calculated before. Okay, and you chug through, you get an answer. Once again, be careful about how many significant figures you quote this to, but also this is a good place to have that little step back and think about your critical analysis. So is a temperature for water of minus 1.2 reasonable? Is that okay? Well, if it was fresh water, no, that is not reasonable, because it would be frozen and the forame wouldn't be able to live in that water temperature, therefore that result doesn't make any sense. But this is, forames live in the ocean is salty, so the temperature of the deep ocean can get down to slightly negative temperatures on the Celsius scale. Okay, so it would have been good to mention that. Now, if you mentioned that later on in your answer to part C, I would have apportioned credit to this part of the question where it was supposed to be. So as long as you're doing that critical analysis somewhere and checking the reasonableness of your answers. I mean, if you came up with a temperature of 4,000 degrees Celsius, I mean, that's not right. Okay, so it's always worth writing down. If you do come up with the answer like that, you can't figure out why, just jot down, this is wrong because water boils at 100 degrees Celsius and 4,000 is not appropriate. Likewise, if you had an answer of minus 50 Kelvin, then that's not reasonable because that's not physically possible. Okay, right, so moving on now to some of the assumptions that we make when we use stable isotopes as temperature proxies. Okay, so once again, so this is an example of where this question, although it doesn't explicitly say, it has multiple parts. So we could kind of maybe split this up even into 3 parts. Okay, so what assumptions are made when we use stable isotopes as temperature proxies? Comment on those assumptions. Okay, and that's quite important because this is this critical analysis element. You know, we make this assumption, but is it important? Does it make a difference? Is it an assumption that is actually really good to make, or is this assumption quite often invalid? And then lastly, why might our estimate of past water temperature be incorrect? Okay. So first of all, the main assumption we make is that the isotopes between the water and the carbonate that we're measuring are in isotopic equilibrium. So that means that there's a complete exchange of isotopes between the water and the carbonate as the carbonate is growing, as the forame is producing its shell. Now, this is an assumption that's quite often not true, not valid, because this is a liquid and our calcite is a solid, so it's actually very hard to exchange isotopes between those. So you only really get isotopic exchange possible as the test is growing. So that would be a good thing to mention. Another assumption might be that maybe the oxygen isotope composition of the ocean, which is kind of surrounding the forame, is not the same as the water that's kind of within or just around the edge of the forame where it's producing its shell. So there might be a small difference there. Now, for forames, this is probably not such a big difference, but for some other carbonate producers, it potentially is. Okay, so that might have been something you might have mentioned. One of the things that we might also want to consider is there some biological offset from our thermodynamically predicted relationship between fractionation factor and temperature. So there might be some Small effects, so different species might have slightly different fractionation factors, and that's kind of reflected in these kind of graphs here. So these different colours are basically experiments done at different temperatures, or samples taken from the wild from different temperatures, and their oxygen isotopes of carbonate and water are measured. And effectively, sometimes we have to do an empirical calibration. So we have to basically, rather than use the pure thermodynamic arguments, we have to go out and basically measure lots of stuff and draw a straight line through it, and then calibrate our difference in isotopes against temperature. Okay, so that might be some of the more kind of the discussion of some of the assumptions that you could have put in. Another assumption that's quite often made in paleoceanography is that the carbonate that the shell that we collect, that's the same carbonate that initially formed when the shell first formed. And quite often that's not the case. So quite often, this is an example, this is a close-up of the surface of a foraminifera, and this is a close-up of the surface of a fossil foraminifera, and you can see here that there's been quite a lot of recrystallization of this calcite. So this is important because if that recrystallization has kind of exchanged oxygen isotopes with the pore water that this foram was kind of like sitting in the sediment, that means that it will have reequilibrated at a different temperature. Okay, so the paleo temperature would then not be valid. Okay, so you could go on and say, well, this is an assumption that we make, but then actually sometimes we can look at images under the SEM like this to check our assumption. Okay. I have no idea what that is. Oh, okay, right. So here we go. So just there's 3, 4, and 5 over here. I apologise for those appearing. That was an error. Why might the estimate of past water temperature be correct? Now, most people got some part of this correct in terms of we made the assumption that the water oxygen isotope composition is the same. Okay. Now, some people got a little muddled up in saying that it's not the same as the global average, but that's not what the question is asking. So we're reconstructing the paleo temperature at the site that foram grew. We're not trying to reconstruct the global temperature from this one foram. Okay, so by saying that there's regional variation, or the surface oxygen isotope or surface salinity might be different. So this is a plot of salinity, of kind of measurements all around the global ocean against oxygen isotopes. That doesn't matter. Okay, it doesn't matter that our sampling site might not be globally representative. What does matter, though, is that at our sampling site, the oxygen isotopes of the water will not have been the same in the modern as it were in the LGM. Okay, and one of the main reasons for that is this here, is that during the last glacial maximum, 21,000 years ago, there was a huge ice sheet over the northern hemisphere. Antarctica was also larger, the ice on Antarctica was larger. So that means that water is held up in the on land, means the ocean is saltier. And just looking at this graph over here, and then let's see if we have a saltier ocean. Okay, we're much likely to have more positive delta 18O, so heavier oxygen isotopes. Quite a lot of you knew the reason for that, in that if we take the light isotopes out due to evaporation and precipitation and form ice sheets from that, that will leave the remaining ocean heavy with respect to oxygen isotopes. So this is kind of the effect of that. So this is actually a graph of the benthic O18 measured in forams. So some component of this changed between now and the last glacial maximum, going towards heavier or more positive delta O18, heavier oxygen isotopes. Some portion of that is because the water has changed composition. Okay, so that would have scored you some marks, and did for many. Okay, so finally now moving on to this last part, so question, well, it was the middle question for me, question 3. We're really asking you here to come up with a sampling strategy and a measurement strategy for determining if the lead contamination in a child's playground is from a local factory. Okay, and the information that you're giving is the playground is built on the edge of a granite intrusion, might be relevant, but it's also next to a factory. Okay, so I think so you need to basically come up with a sampling and measurement plan. So importantly, to get the good marks here, is this key where you have to justify all of the choices that you make, and that was actually part of the question that was mostly answered at the worst of those that attempted this question. Okay? So most people came up with reasonable ideas about where they would sample, what kind of measurements they would make, but it was really justifying those decisions that was not so good. Okay, so things you might want to be thinking about. That was actually defined in the question. What's the sample type that you're going to measure? Where are you going to measure the samples from? And the analytical techniques you're going to use. Okay. So again, so quite a lot of people didn't draw a diagram for this, which I thought was odd. It would have been a very quick and simple thing to do, just to demonstrate where you think you're going to sample from. If you just drew a sketch map of what you think the arrangement of kind of the playground, some factory, and some granite intrusion, what their spatial relationship was. I mean, you could have made it up. It doesn't have to be, precise to what I was thinking in my mind when I read the question, but just to demonstrate how you would go from what you think the arrangement was to a suitable sampling strategy. Okay, so before we come up with a sampling strategy, we need to come up with basically some kind of hypothesis to try and test. Okay. And we also then need to make sure that the measurements that we will propose to make will be able to answer the question, which is where has the lead in the playground come from? Okay, so we might want to think about this kind of second thing. What are the possible pathways for the contamination? So we could have lead coming in maybe in aerosol form, so dust from the factory coming down into the playground from the atmosphere. It might be some groundwater contamination. Okay, it's unlikely with lead. But you would outline what you think the root of contamination is, and then come up with some way of sampling that root of contamination to show that it's either coming from the factory or it's not. Okay. So one thing that you could have done is you could say, well, I think it's the root of contamination is atmospheric. So you could put some atmospheric samplers out that maybe sample the dust in the atmosphere every couple of hours or something like that, and then you measure the lead content in that dust, and you might want to measure it kind of close to the playground, but also if you just measured it close to the playground, you could see maybe that you get spikes in lead contamination at some times during the day or sometimes during the week. But if you wanted to attribute that to coming from a particular source, you might want to have a measuring station that's closer to the source than your playground. Okay, so therefore if you could correlate the variability in the lead concentration between these two stations, that would indicate that perhaps the factory is a source of lead to the playground. Okay, a simple correlation wouldn't necessarily prove that. It might be that the playground is providing lead to the factory, but having some reasoning for your choice of where you put out your samplers, that is important. Go forwards. Yeah, so you could have had a slightly better sampling strategy if you also sampled, in a distal location that's far away from the factory, to show, perhaps test the hypothesis that maybe the lead is a regional input from kind of factories all around the world that are putting lead into the atmosphere, and that's raining out. So you might want to expect, if the lead is coming from this factory into this playground, you might expect there to be a better correlation between these two sites than there is between this site and this site, or this site and the playground. Okay, so you think about how you would basically, the important thing is how you go from some data to being able to answer the question about where the lead is coming from. So quite a lot of people discussed sampling from the soil. So the bare minimum, I think, was a sample of the playground, a sample of the factory, and then you'd measure the concentration of lead somehow. Okay, so this was kind of along the right track, but it's not really sufficient to be able to test where the lead is coming from. Okay, so imagine these are our results. Okay, we get higher lead near the factory than the playground. I don't think that necessarily we can use that to say the lead is coming from the factory. I mean, if we had high lead at the playground, high lead at the factory, that still doesn't suggest that lead is definitely coming from the factory and not from the granite intrusion. Okay, so we might need to think about having a more detailed sampling strategy. Okay, so we might decide to have one further away. Okay, so that might, if we have lead that's high concentration over here, if it's high concentration everywhere, then that might suggest that it's not coming from the factory. Okay, but if we have a low concentration far away from the factory, then that might suggest that these higher concentrations near the factory are more from the factory than not. So obviously that's still a little bit inconclusive, so we could fill in that with maybe some transects or grids of samples, and look at gradients of contamination, and using the gradients of contamination you can basically start to identify whether places are being sources of contaminant or not. Okay, so being able to show what your expected results might be and how those will be able to tell you where the lead is coming from would have been a good thing to do. Okay. Another approach could have been sampling down core. So if we had produced maybe a sediment core near the playground, if the contamination is coming in via an atmospheric route, we might expect there to be more lead near the surface, where if it's coming in from kind of the geology, so the weathering of rocks and formation of soil, it might contain some minerals that have got lots of lead in, then we might expect to have a concentration profile that looks maybe something a little bit more like this. Okay, more even concentrations with depth, maybe some enrichment at depth, maybe not. Okay, because you've got to remember that there might be some processes that might be acting within the soil to concentrate concentrations at any one particular depth. So that's the kind of place where you could bring in this critical analysis and say this is what we might expect, but there might be these confounding factors that hinder our interpretation. One way of really nailing down whether the source is from one place or another might be to use isotopes, and a few people did this. There's a little bit of confusion about what you would actually be trying to do with the isotopes. So quite a lot of people were trying to date the age of contamination, whereas the age of the lead in the factory could be any age depending on where the lead ore was sampled from or collected from or mined from, whereas the granite could be almost any age as well, so it could be very recently emplaced or very old. The key thing is that it's highly likely that, because unless this factory is processing this granite, it's likely to be processing samples, material from somewhere else in the world, so it's very likely to have a different lead isotope composition. And the good thing about lead isotopes, there's a number of different ratios you can plot up, so it's not just one set of isotopes, you can plot up another set of isotopes, and then if you measured some, maybe you don't have to measure as many this time, you could do a smaller number of samples perhaps, measure some samples from the playground, and if they plot up towards the composition of the factory, that suggests they're coming from the factory. If they plot coming more towards the natural local lead signature, then you might expect them to be from there. And if they, that's kind of the first level of kind of interpretation, but actually if you measure a bunch of samples and they show a mixing line between the two, that's quite useful as well, because that means you can work out what proportion of lead is perhaps coming from one source and what proportion is coming from another, which is actually very valuable when you're trying to attribute the amount of pollution from somewhere. Okay, they were in the wrong order. Okay, so quite a lot of people came up with a sampling strategy. They said they would measure it somehow, and we'll come on to that in a bit. But very few people thought about exactly what kind of samples they would measure. Okay, and this was really important as well. So would you take the soil sample and dissolve all of the soil? Would you just do a leach of the soil? Would you sample just some of the biology growing on the soil? Because that might pre-concentrate your lead, make it easier to measure. So that kind of aspect of the sampling strategy in terms of what you do with the sample once you've plucked it out of the ground. What is it that you're actually sampling? Is it soil? Is it rock? Is it plant matter? Okay. Is it children? Don't measure. Well, you can measure children. You could particularly measure the lead content in children's hair or bones or whatever. You could grind up the children. Don't grind up the children. Okay. Now, analytical technique. So this was probably the part that was answered perhaps the best of all of this, but still there were places which could have been improved. So really, if you wanted to measure the lead concentration, there were a whole bunch of variety of techniques that you could have used. You could have used XRF, so X-ray fluorescence to detect trace element concentrations of lead. You could have used ICP OES, so an optical emission spectrometer to detect concentrations, or various kinds of mass spectrometer could have been used to measure the concentration. Just to point out that if you had gone down that route and said, I'm going to go and measure the isotope composition, that might be you might be able to justify that by saying, oh, I need fewer samples because I need 3 samples to see where the lead is coming from, rather than if you want concentrations, you might need a whole map of samples. So if you're going to measure the isotopes, then you need to use some kind of mass spectrometer. Okay. If you're going to just measure the bulk samples or leaches from samples, it's probably best to use an ICP MS, because these techniques, well, TIMS, you need to do a lot of chemical processing on that to get just the lead and remove the matrix. And SIMS is best. Well, SIMS might have been appropriate if your sampling strategy was, I'm going to try and identify the minerals present in the soil that have got the lead in them, and that might tell me something about where those minerals have come from. Then it might be appropriate to use an in situ technique like SIMS, where you might be trying to identify where in or around on the surface of a mineral grain the lead is actually based. Okay, so once again, really have to think about justifying which techniques you're going to use. Okay, so when you do that justification, these are the kind of things you need to be thinking about. If you're going to use ICP-MS or XRF, you need to think about detection limits. So maybe the XRF would be good because it's kind of accurate, it's very cheap, you can put through a lot of samples, doesn't have any instrumental memory, very little sample preparation is required. But if the concentrations are too low, then you might have to go to an ICP technique, which will have slightly better detection limits if you're using the mass spectrometer version. So these are the kind of things that you need to have mentioned that you would consider, okay, whether you would use one or the other. Okay, you might end up doing, I'll do some measurements by XRF first, just to get a picture, and then go back and fill in the detail later if the concentrations are low with an ICP-MS. So you really have to go through and justify your sampling strategy and your measurement plan. Okay, it's this justification step which is the important part of this question. Okay, so once again, just to recap, that's kind of what we're looking for here. We're trying to devise a plan and justify that plan. That's what's really important. Okay, so hopefully this has been useful for you. 3 questions there, quite different styles of question, but the really important things is getting you to answer the specific question that we asked. Go through the question and find out which are the parts of the question. So even if it doesn't say A, B, C, there will be parts within the paragraph of question that you need to answer individually. And just going that little bit beyond, getting the answer and then thinking about that answer. Is it correct? What are the assumptions? What alternatives could there be? Okay, that critical analysis of basically how to get the good marks. Okay, so yeah, I hope this has been useful. I certainly had fun making it. Yeah. Anyway, end of show.